Thanks for the introduction and good afternoon, everybody.
Good afternoon.
We are presenting the current status of task 5.1 in this SCCR, which is focusing on the assessment or evaluation of energy storage technologies and the application. This is a collaborative activity of the Technology Assessment Group at PSI, University of Geneva, and the University in Lucerne. And what we are going to present now is a short overview in terms of who is doing what. A few words about the methodological framework for the evaluation of storage technologies. And then we will focus on the two first case studies we are carrying out. The first one is on power to gas, and the second one is on application of batteries as storage technologies. So our main goals are the two here. First, develop a consistent methodology for the evaluation and assessment of storage technologies in the Swiss energy context. And the second one is then based on this methodology to actually carry out the assessment or evaluation of storage technologies and in the context of the overall energy supply system in Switzerland. Apart from that, one other goal is the improvement of the flexibility between power and heat in Switzerland. And as all SCCRs are supposed to collaborate and share knowledge and increase knowledge sharing, that's also part of our work.
Okay, so as Christian suggested, we are a team of 3 different research institutions here, and in the case of Lucerne, they are focusing on electrical thermal energy storage and energy storage applications for industry. In my case, coming from the University of Geneva, I am focused on techno-economic analysis of different energy storage technologies. And today I'm going to present 2 case studies, one for hydrogen and another for battery. I know that there are people here working in hydrogen, others working in battery, so hopefully I can attract the attention of both sides.
Okay, so University of Geneva is basically dealing with the economics of the system, and PSI here is carrying out life cycle assessment, means we are doing the environmental evaluation. So a few words about the methodology. Well, we heard already today that evaluating storage technologies as on their own doesn't make sense because they are always embedded in the system and only have a benefit in the energy system in the larger context. So we are defining an reference energy system with mobility, industry, and buildings and district. Then we have some energy demands in terms of electricity, heating, and cooling, and we have different types of energy supply. And in between, we might have energy storage. And what we are interested now are the benefits of this storage, and the benefits or drawbacks can depend on different types of application. And what makes it more complicated is that all that depends on different scenarios. That depends on the development on the future development of the storage technologies. It depends on the price of electricity, for example. It depends on incentives, subsidies from the state, and so on. And all that we are considering then in the end in our final evaluation framework. And as I said before, those 2 things are our focuses. Well, we focus on techno-economic assessment, that is the job of University of Geneva, and on the environmental assessment in terms of life cycle assessment, LCA, that's our job at PSI. So this slide you have seen already before, so I'm glad that I don't have to explain it again. Our first study, case study, is dealing with power to gas, which is located here. So power to gas is meant as a long-term energy storage, which can even level out seasonal fluctuations. And yeah, that's one of the case studies we have started with. There are 2 reasons for that. First is that within our work package 5, there's a group at Hochschule Rapperswil who are installing a demonstration plant for power to gas applications, so we have direct access to data. Also, a group at PSI is dealing with electrolyzers and with methanation, so we also can get knowledge there. and those are definitely advantages for a technology assessment if we can access the data directly from the hardware developers. That here shows you basically the system layout of a power-to-gas system. You have the input of electricity for the electrolysis. You can use the hydrogen directly, for example, in a car, but you can use it also for in a fuel cell for stationary application. You can use the hydrogen then together with CO2 and generate synthetic natural gas, which you can either feed in the natural gas network or again use it as a car fuel, and there are different other applications which are not here in the graph. So it's quite a complex system in terms of assessment. What makes it even more complicated is that for each of these processes you have different technologies. Like, as we heard before, you have PEM electrolyzer and alkaline electrolyzers. There you have different, or you can have different sources of CO2. You can have different methanation process, and all these different processes will make in the end a difference in the results of the assessment. Okay, so how are we dealing with or how are we carrying out now our life cycle assessment, calculating or quantifying the environmental burdens of here the final products? Well, we collect input and output data for all these individual processes, like energy demand, material demand, process emissions. Then we connect all these different processes together, and based on that we can calculate then the final cumulative environmental burdens per unit of methane, per unit of hydrogen, and compare that to the conventional supply methods like steam methane reforming or fossil fuel extraction. So I won't go more into details about LCA methodology as such, but directly jump to the results because I think that's what you're interested in. So what is shown here are the greenhouse gas emissions for hydrogen production. Here you have the conventional steam methane reforming, and here you have different types of electrolysis and different types of electricity supply for the electrolysis, so wind, PV, and the Swiss electricity from the grid, and the European electricity mix. And what you can see here that the greenhouse gas emissions per megajoule of hydrogen generated, they are lower for those generation pathways, but they are higher for these two generation pathways compared to the steam methane reforming. So that shows that really the electricity input to the electrolysis, or the source of electricity which is used for the electricity input to the electrolyzer makes it a big difference in terms of environmental burdens from this electrolysis. Okay, this one shows you the greenhouse gas emissions for natural gas combustion. Here the conventional natural gas supply. Here different types of power-to-gas technologies. Here with PV electricity supply to the electrolyzer, here with wind power electricity supply to the electrolyzer. Then the difference between those two and those two on the other hand is that represents the best case and that the worst case, so to say, in terms of source of CO2 for the synthetic natural gas production. That's from a wood combustion power plant, and that's from cement production. And all the other sources of CO2 are in between those two in terms of greenhouse gas emissions per energy. So what this shows you is that the additionally to the source of electricity, which is different here and here, also the source of CO2 makes a big difference in terms of environmental performance of power-to-gas. Then power-to-gas fuel used for mobility in terms of greenhouse gas emissions per kilometer traveled. Here you have a vehicle which drives with a conventional natural gas supply. And here you have vehicles, passenger vehicles, which are fueled by different power-to-gas technology combinations. All of them get their CO2 from wood combustion, so remember that was the best case. And here you have different types of electricity supply for the electrolysis. And what you can see here in the end is that, well, the conventional car isn't that bad after all, if you compare it to those three types. I mean, you really have to select a good technology for combination for power to gas to be substantially below the conventional natural gas vehicle. And this shows you why. Again, here then the conventional natural gas vehicle, these dots always represent the total emissions per kilometer traveled, total greenhouse gas emissions per kilometer traveled, and those different parts of the bar, the different process contributions. You can see here that if you capture the CO2 from the atmosphere or the CO2 from wood, which is capturing indirectly from atmosphere, then you get some negative contributions. And those allow you to get a slightly better result than for the natural gas, for the conventional natural gas car. And what needs to be emphasized here is that this electrolysis here is carried out with PV supply. So you can get better if you take, you can get better in terms of greenhouse gas emissions if you take electrolysis from wind, for example, from wind power or from hydropower, but you can get also much worse if you take electricity from a natural gas power plant, for example. So that was basically my part.
Okay, so it's my turn. Before entering into details of techno-economics analysis of power to gas, what I'm gonna do is explain what are the specific characteristics of the techno-economic analysis we are performing here, what it makes different to others. I think that an important detail is that it is based on simulation, on dynamic simulation. And this is important because energy storage is used normally to mismatch renewable energy and demand. So it's important to capture the dynamic of renewable generation, of the demand, and of the energy storage itself. Another important point is that consider the whole life of the energy storage technology and the aging of the technology. We have already have some insights of aging, of battery, and even of electrolyzers this morning, and this can have a great impact on the results. And the final characteristic of our analysis is that it is focused on Switzerland. So I will start now with the results regarding power to gas. So as my colleague has explained, we are going to compare two available technologies at the moment. One is alkaline electrolyzer and another one is PEM electrolyzer. We have had this afternoon explanation about the polarization curve. You can see the cell voltage for us versus the current density in the horizontal axis. And the main difference here is that for a PEM electrolyzer, it can reach much higher current densities, but also the voltage is lower. For example, if we compare the voltage around here, around this current density 0.3 amperes per square centimeter, the voltage for alkaline is around 20% higher than the voltage for PEM. So in principle, PEM electrolyzer is able to perform at higher power density, but also with higher efficiency, because the higher the voltage, the lower the efficiency. So considering that, and this is the performance that I am considering, this is the operational point for two electrolyzers. Typically, they perform at high current density, so they are hot, and they can operate with high efficiency. These are the results for those technology. In this case, is for a 10 megawatt hour electrolyzer. Is performing, the gas is introduced into the natural gas network. What are the most important things to consider? First of all, the stack cost. PEM is more expensive than alkaline. And a very important detail to consider is the degradation, because many of the results in the literature are based on nominal values. What does it mean? That are based on the initial values. But this is a dynamic technology that is going to last for 10 years maybe, so it's important to capture the degradation. This is the input data for the durability, and according to that, this is the efficiency, and this is the consumption to generate 1 cubic meter of hydrogen. Here, maybe I want to suggest that there is not such a big difference in terms of for PEM and electrolyzer. The difference here was bigger, and this is due to the degradation. The modeling is capturing the degradation of the technologies. So this was more from a stack perspective. Now I'm going to move into a system perspective. So this axis represents the levelized cost of generating the gas. This axis represents the capacity ratio. And here we have the electricity wholesale price. This is the electricity price in the market. So I'm going to use this techno-economic analysis to optimize the price that the electrolyzer should run. And we will see that here we have a very interesting trade-off. For example, what happens if the electrolyzer runs whenever the electricity price is lower than 55, for example? We are having a very nice capacity ratio. This is very good, but at the same time, the levelized cost is quite high because the electrolyzer is using very high electricity at some times. Now we go to the other limit. We go to a very low electricity price. This is on the one hand nice because the raw electricity is cheap, but on the other hand, the electrolyzer is only running not many hours every day. So we can see that the capacity ratio is not very high. So there is an optimum, and for alkaline is around 43 Swiss francs per megawatt hour, and for PEM is a bit higher. Why is higher for PEM? Basically, we are having a bigger investment, it's more expensive. We need to use the asset, we need to use the electrolyzer a bit more in order to optimize it. So here we have discussed the optimum price for the levelized cost of the production of the gas, and now we are going to move into another interesting techno-economic parameter. First of all, the system efficiency, and then the levelized cost as a function, the electrolyzer rating. This is a logarithmic scale, and we are ranging between 25 kilowatt, which is the size of the pilot plant in Rapperswil, to a very big system, too big even for Switzerland, I think, 1 gigawatt electrolyzer. So here we have the system efficiency for alkaline PEM when they generate either hydrogen or methane. Here CO2 is used for methane generation. And here we have the levelized cost. We can see that there is a positive effect on the rating. Regarding the system efficiency, what is happening is that the balance of the plant, when the rating decreasing, is becoming relatively less important. And in the case of the levelized cost, we also have, in addition to the efficiency, economies of scale. If we compare, for example, hydrogen versus methane, for generating methane, we are introducing a new system. We are introducing a methanation reactor. This is reducing the efficiency, and in addition, we have an extra cost. As a consequence, the levelized cost is a bit higher for that technological option. Again, alkaline results are a bit better, and here I want to draw your attention to steam reforming. This is the cost of generating hydrogen with the steam reforming, still lower. But we are only looking at one aspect here, at the cost. Now we are going to look at the value of energy storage, and this has already been introduced this morning. The value is related to the revenue. So here, for 1 megawatt electrolyzer, we have the levelized value, which is the revenue, considering again the efficiency at the whole life of the system, and the internal rate of return as a function of the value proposition. This means as a function of the different applications that the power-to-gas plant can perform. As it was suggested, this is an enabling technology. It can perform more than one thing. For the reference, you have here the levelized cost. As it was suggested before, only generating hydrogen, in this case, even with the premium due to the renewable energy supply, because in Switzerland the energy mix is quite green, is not enough to be higher the value than the levelized cost. But what happens if we introduce more applications? For example, the heat is harvested and used in the area, if this is the case, if this is possible. This is not enough to create a business case. But if we introduce these applications are described by these different economic input data: frequency regulation, the possibility of using oxygen, also the CO2 emissions. Here is when the levelized value is increasing, even higher than the levelized cost. And as a consequence, the profitability that at the beginning only with hydrogen was very negative is becoming positive. Here, I want to suggest that this is a maximum potential, because at the moment, I am not introducing the extra cost of making use of the heat. Here, maybe I need to engage with more manufacturers or stakeholders to know specifically what is the extra cost of adding a heat exchanger for using the heat, of capturing the oxygen. So this is, we saw before the cost, now we have seen the value and the profitability for power to gas. Now I'm going to digress for a moment, and in this work package, what we have developed is a uniform energy storage assessment. So the idea is to use it with different technologies, with different applications, and I'm going to give an example of that. So in this case, we changed totally. We are talking about battery storage for a single home. Before we were focusing on a bulk energy storage on a large scale. Now it is a small scale distributed. Here the context is Geneva. The results that you will see here is for Geneva. But we have made results for the Jura region, which has the higher electricity prices in Switzerland, and for Germany for comparison. So we are going to compare lead acid and lithium. Here you cannot see the details, but there is an aging model again. But you can see, for example, in this table, that the cost of lithium ion is 2.5 higher than the one of lead acid. Another assumption, with the PV electricity, we can do, for example, we can supply to the home appliances if there is instantaneous generation with the demand. We can export to the grid, but that export is at the wholesale price. It's the price of the market. Or we can storage and use it later at home. And with that, we are replacing grid import, which has a much higher price. I will give you a figure. For example, in Geneva, the price of the kilowatt hour is 20.5 cents per kilowatt hour. The average price of the wholesale market is around 5 cents per kilowatt hour. So it makes much more sense to use that electricity at home than to export to the market. This techno-economic analysis can be used for different things. Before, we saw that we optimize the price in the market for power to gas. Here, we are going to compare the battery performance and techno-economic for different tariffs. The first one is a single profile tariff, which is the one that everybody has at home. It's a constant rate. And we are compare that with a tariff that it was created, is not available in the market, but is based on the price on the market. So it's one price per hour reflecting the real price of energy. So we created that tariff considering the different structure of the tariff, the network cost, the incentives, and we include that to the energy, to the price in the energy market. So we did that for lead acid and lithium ion. These are the performance results. This is the amount of demand of the house which is made by the battery. This is the round-trip efficiency, and this is the equivalent full cycles. What is happening here? With the dynamic tariff, is variable. So again, the battery only discharges when the price is high. So we can see that the equivalent cycles reduces regarding the simple tariff. This is the simple tariff, and this is the dynamic tariff. For example, we can also see these results as a function of the battery capacity, how lithium-ion technology is more efficiency than lead acid, and how it's able to meet a bigger percentage of the demand. So based on these performance results, now we are going to compare the same. We are going to compare the levelized cost, the levelized value, and the profitability, but in this case, for another application. We have here, as a function of the battery capacity, this is the normal range for a house. We can go small for a 4 kilowatt hour or very big for a 20 kilowatt hour. You have the levelized cost, the levelized value, and the internal rate of return. So here I want to draw your attention that that with the dynamic tariff, the levelized value of the discharge is much higher. And this is related with the dynamic tariff is reflecting the price in the market. So, for example, in the evening, if the price is higher, there is, the discharge has a higher value because it's reflecting that fact. In the case of the simple tariff, it's a constant price. In the case of the levelized cost, on the contrary, with the simple tariff, we are reducing the levelized cost because the tariff is discharging more frequently. And the internal rate of return is a balance, but in this case, with the simple tariff, we are obtaining higher internal rate of return or return values. Specifically for a 12 kilowatt hour lithium-ion battery, we have almost neutral in Geneva. Previous results in the Jura, we have positive internal rate of returns because electricity prices are higher, and even in Germany, we have internal rate of returns up to 40%, up to 4%, sorry. So I'm not gonna enter into details here, but we are also performing sensitivity analysis because these results depend on the input data, cost, durability, and there are great variations. So in order to tackle the uncertainty of that, we need to perform sensitivity analysis. For example, here you can see when how results change against the cost, the life of the battery, the discount factor, the retail price. Obviously, the cost has a huge impact on the results. So the levelized cost, but also the internal rate of return, are most sensitive to the cost. But the retail price is also quite important. So I'm gonna make some conclusions regarding the two technologies that we have described today and how this techno-economic assessment has been used for different purposes. According to the simulations and the results that we have seen, alkaline electrolyzers offer a better levelized cost, still higher than hydrogen generated by steam reformation, but we have seen that a power to gas can perform more applications and increase the value. Regarding power to methane versus power to hydrogen, the power to methane increases the levelized cost between 15 and 30%. So in principle, power to hydrogen is more interesting, but we should consider that in the line, we can only fit at the moment 3% in volume, and the most optimistic projections increase that value up to 10%. So this is a limitation that we should consider. Hydrogen is more efficient, better cost, but we have a limitation on the transport. We have optimized the wholesale price condition for those technologies, and this is an interesting result. And here we saw that a power-to-gas plant needs to perform several things in order to have an internal rate of return positive, in order to increase the value.
Okay, concerning the environmental performance of power-to-gas, only a few words because we are running out of time. So the two main impact factors are definitely the source of CO2 for the electricity and the source of CO2 for the conversion to synthetic natural gas. We've seen that under certain circumstances, power-to-gas with renewable energy can perform better in terms of greenhouse gas emissions compared to conventional fuel supply. But what I've shown you right now is not the final answer. We have to carry out further sensitivity analysis, and more important, the results depend on allocation procedures and system boundaries, so we will look into that more closely.
To finish, just in the case of the battery, the main idea I want you to take that again, the dynamic tariff increases the value, but it's necessary to perform more things. Especially the battery needs to discharge when there is high value associated. So this is work related to batteries with hydrogen, but we are looking forward to work in other technologies with other colleagues in SCCR storage. So,
okay, last slide, only one comment concerning the long-term goal. Well, until right now, we have only evaluated certain storage technologies in a very specific context, but our long-term goal is definitely the evaluation, trade-off analysis of different applications of different storage technologies from the Swiss perspective. So the embedding of the storage technologies in the whole Swiss energy system.
So thank you very much. And if you have any question.